Hello and welcome to our discussion of Chapter 11, Cloud Software as a Service, SaaS Service Model. This is part of ISOL 536 Security Architecture and Design. My name is Dr. Alan Dennis and I'm your instructor. Jumping right into the discussion. Chapter 11, Cloud Software as a Service, contains the following sections. We're going to start off with what's so special about clouds. We're going to then talk about, do some analysis around pilling the onion, freemium, demographics, protecting cloud secrets, the application in defense, and globability, and additional requirements for the software as a service reputation service. Jumping right in, what's so special about cloud? So cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, example, networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. In the mobility example, we present the management of the mobility clients and reputation service as servers in the cloud. Of course, these services require far more architecture than a single server or a single or horizontal scaled set of servers. So to keep in mind, there's also several other components of cloud computing that kind of figure into it. The definition there is pretty good. It misses the point to where we typically expect the pricing that we pay to be based upon our consumption, so consumption-based pricing. We also truly expect self-service so that we can, with almost no interaction with the cloud provider, do it ourselves, if you will. This kind of talks to it a little bit whenever we talk about minimal effort of the service provider interaction. It's about self-service, but it's beyond kind of just that. We expect to be able to log onto a portal and create a service, start using that service with no interaction with the provider at all directly. 11.2 is around analysis, and we start peeling the onion. From our perspective, we need to know that data are pulled and received from many sources via a data input function. That function, like the data gatherer in the business analytics example, must normalize and process many different types of data so that the data may be kept in a unitary fashion that can be processed for reputations. One logical function, therefore, is the receipt and initial processing of the various data types. Neither the figures of the SaaS architecture in this chapter portray reputation data collectors, so it's being excluded from discussion. And figure 11.1 represents the cloud service as it may look logically from the user's, that is, the mobile security software's perspective. The cloud means that the service has multiple points of presence across the globe to be queried. Cloud also implies large scale to support thousands, even millions of clients. The mobile device software doesn't need to understand any of the details behind the service. In other words, the detail of retrieval, processing, rating, and responding to queries are entirely opaque to the querying software. And oftentimes that is accomplished through the use of services that abstract out all of that complexity behind, and you simply know how to talk to the service. The freemium demographics in section 11.2.1. One standard method of dealing with the fact that authentication does not protect against all attacks is to log the action taken on the system by the authenticated entity. Logging system activity is a typical additional control. Monitoring is often employed so that at the very least, malicious actions can be tied to a user of the system. In order to monitor the activity, first must be logged. At best, instantaneous initiation of malicious actions will be noticed and can be stopped before serious damage takes place. For social media sites, logging of action sequences is critical to identifying malicious users and ejecting them from the system before they can harm other users or the system itself. Since the reputation service, we understand that attackers can gain access. All actions taken place on the service by each device are logged. Anomalous sets of activities trigger an investigation from the 24/7 around-the-clock security monitoring team. In figure 11.2, you will see the authentication service as in the e-commerce example, the architecture has placed the authentication service within its own highly restricted network segments. Only the front end may issue authentication requests. In this way, the authentication service cannot be attacked from the internet. First, the front end would need to be compromised. A key concept whenever you're dealing with things like logging is that it's not just about logging and preserving to a file. Generally speaking, you want to process that log as quickly as possible in some sort of streaming fashion so that you can respond sooner than later whenever malicious activity is being detected. Moving on to 11.2.2, protecting the cloud secrets. Um, there are certificate chaining validation methods that address this problem. And indeed, if the enterprise customer requires a separate signing key, and almost all will, then your cloud reputation service will have to employ a fairly sophisticated certificate signing and validation implementation that accounts for multiple certificate signing keys. Still, messages from the service may be signed with the same private key so that each device can employ the public certificate key to validate. 11.2.3 is about the application is a defense. Even the best, most security conscious development teams occasionally allow serious security vulnerabilities to leak out into production software. So how can a service like the reputation service ensure that all non-valid input is rejected? Security software testing is beyond the scope of this book. Still, it may be worth mentioning that a typical testing strategy is to fuzz inputs that are likely to receive misinformation messages from other input data. When we examine the file processing chain in the endpoint security example, fuzzing was one of our recommendation security controls. This software must be made to withstand poor inputs. It will be examining malicious files. In a similar way, the reputation service front end, which must receive requests from possibly malicious sources, will benefit from rigorous fuzz testing. In order to protect services further within the chain of processing, the reputation service will want the front end to be as bulletproof as possible. Fuzzing is an accepted testing methodology to ensure robust input defense. The sequencing of processing goes something like the following. First, a device requests a reputation for an object. The query response processing front end requests a reputation from the reputation processor. The reputation is returned to the device. It is also placed in the cache for rapid retrieval should a subsequent request for the same information be made. New data comes in about the object. In the backend data store, the object reputation changes. The reputation triggers the reputation processing component to check the cache for the presence of the reputation. If found, it's still in the cache. The reputation in the cache is deleted, forcing the front end to refresh the reputation when it's next queried. And it's essentially cleansing the cache of what is now stale information. Moving on to section 11.2.4, globability. In figure 11.2, which you see there to the right, you will see that the backend is not discrete but connected and replicated to all the points present across the globe. This is very typical for global software as a service services. It's desirable to keep processing as close to the consumer as possible. Consequently, all of the reputations must be replicated to each point of presence. This means that across the globe in each data center, the host that host the service, the front end processing service, and the reputation data are duplicated. If the reputation service is to be accurate everywhere, this replication of data has to be very fast so that the reputation query in Singapore is as accurate and up to date as the query in London or Hawaii. This need for the rapid dissemination of updates and rigorous duplication of data everywhere implies the backend can be thought of as one global system rather than discrete points. At the backend, all of the systems are connected as they must be to achieve the performance and accuracy requirements from a global cloud service. And in fact, most global service providers, internet providers, cloud services, have mechanisms in place for global redundancy. It's not necessarily cheap, but it is there and it is quite fast. And in fact, a service like Cosmos DB, which is a multimodal NoSQL database system, guarantees sub-second synchronization around the world. So pretty amazing stuff. And it's essential because you don't want somebody to be making decisions off of stale data, and stale is dependent upon the problem domain. Sometimes being a little slow is okay, being overly slow may be problematic. So establishing what that service level requirement is essential, because it's not going to be cheap if it's very high. So it's important to understand this. And in fact, most of the time when you're dealing with these sort of services, you don't really even think of it as in the sense that it's a global set of services. You think of it as one thing that happens to be distributed around the world. Continuing the discussion of 11.2.4, there are three architectural patterns that seem to be emerging to provide sufficient tenant data protection. Encrypt data as it enters the service, decrypt data when it exits. Encryption as data enters the service, and decryption at exit is the preferred solution from the customer's perspective, as long as the keying material are held by the customer and or the customer's trusted third party. And that's where the concept of bring your own certificate comes to play. And generally speaking, you want data to be encrypted at all times. Whenever they say it's decrypted as it leaves the service, what that would mean is it's decrypted so that it can be encrypted to go over the wire. You don't ever send things out, generally speaking, in the clear. Separate processing within the infrastructure. Each customer essentially receives distinct infrastructure and processing. Separation at the infrastructure layer is very popular within services that offer a platform and infrastructure, that is, platform as a service or infrastructure as a service. Each customer essentially receives distinct infrastructure and processing. That, or it appears to be that it's the case. It may very well be that it is distinct virtual infrastructure and processing. So whether or not it's a distinct set of hardware is a different question, but it may very well appear to be distinct, and to the extent that it's impossible to determine if it is not. Encapsulated data such that it remains segregated as it is processed. If the vendor requires economies acquired from building a highly shared application, many SaaS vendors try to reap these economies, then the simple, obvious solution will not work. It is possible now within even shared computational systems that there is isolation essentially during processing. This is made possible by some advances in processing technology at the chip level, literally, so that even within a given chip, there is isolation available even if you're processing multiple workloads. There's a time that that wasn't the case. It's emerged over the past year or so that it is possible in certain cloud providers to ensure that not just that processing is occurring on separated processing hardware, but potentially even if you're using shared hardware, the individual processors may very well provide their own degree of separation. 11.3, additional requirements for the software as a service reputation service. The following list of requirements focuses on the different cloud aspects of this architecture. Earlier chapters covered some depth of other aspects, covered in some depth the other aspects such as endpoint requirements, web requirements, and administrative needs. The calculation processor will not read the reputation cache. A message will be sent from the calculation processor to the cache to execute a delete of all references to an object in the cache. Failure of the deletion will be logged. No acknowledgement will be returned by the cache in response to the deletion message. And instead of deletion, it may very well be an expiration message is probably a better way to say that. And basically, whenever you put things into a cache, the general procedure you do is you say how long it's good for, so it's got a life to live. And what you would do, rather than physically deleting it from the cache, you set that deletion time or the lifetime to be pretty much now or even into the past, so that the next request for that item would sense that it's out of date and force it to be retrieved and loaded instead. The reputation request messages must be constructed by the web front end. Only the queried object will be passed to the calculation processor. So one of the things we're trying to do here is avoid using the cache during processing and potentially be using stale information to improve performance of the processing. It seems a bit overkill because if the cache is being managed effectively, it really shouldn't matter too much, but it is a secure way of doing things. the way that it would be done instead is that the information that's being utilized to construct the reputation cache, any additional information would invalidate or expire anything that happened to have been cache related to that object. The front end will sanitize and validate messages from the mobile devices. Any message that fails validation in form or data must be rejected. That's a reasonable sort of approach. If something isn't in the right format, doesn't pass various validations, it certainly should not be accepted. And sometimes that can happen through legitimate, not necessarily malicious sort of situations. Sometimes messages are interrupted as they're being transmitted across the internet. Sometimes things happen that should never happen. So it's a reasonable expectation in general, not just for security reasons. Before reputation requests will be received, a device certificate signed by the private key of the reputation service must be validated by the reputation front end. Certificate validation failure must cease all further communications and probably should be logged somewhere. All customer reputation requests and request histories will be encapsulated within an unpredictable token. The token will be related to a cryptographic hash. The hash is the only value to be associated to the service tenants. The hash to client relationship must be kept in a separate network segment under separate administrative controls, different teams, from the application administration team and from the storage and data administrators. Hash to token correlation will be done by a separate process running in the back end, unexposed to any process outside of the internal back-end networks. Whenever stored, tenant reputation histories will be tagged with the token only. No mention of customer identity will be placed within that administrative domain or network segment. And this is all about separation of concerns, separation of duties, ensuring that no one person can do something that would potentially compromise the stability or security of the system. Reputation data will be pushed from the data farm on the internal network to each reputation data instance. Reputation data instances will exist on a segregated network that only receives requests from the reputation calculation and processing modules. There will be 4 distinct layers shown in figure 11.2, a DMZ, Bastion layer containing the web service termination. Authentication of device certificates will take place before a reputation request may be made. The front end module that validates requests before any processing may occur. Requests will be regenerated before they are passed on to subsequent layers. Objects about which a reputation query is made may only be passed from the front end after careful validation and format check. The reputation cache is placed on this segment. It receives requests only from the front end. The reputation calculator processor, which only receives requests, reformed requests from the front end. The local reputation instance for a point of presence, which only receives requests from data from the calculation module. The front-end request processing input must pass rigorous fuzz testing before release. The calculation module request handling processing chain must pass rigorous fuzz testing before release. A HSM will be employed at each node to perform certificate, message, and data signing operations. Multiple private keys, including customer-specific keys, must be supported. Every node must validate every device certificate. And with that, we reach the summary for Chapter 11. We've discussed an architecture specific to global cloud products that with many points of presence in the network interconnection. One way to achieve this is to establish a series of connections using VPN or IPsec tunnels over the internet. From a performance-sensitive SAS, the vagaries of internet routing will influence transmission times. Hence, although essentially secure across the hostile internet, such an architecture is likely to be unsuitable for this purpose. Instead, where performance and security must be served, a private network is often the better choice, or at least something that looks like a private network. It may actually be a virtual private network. And with that, we conclude our discussion of Chapter 11. If you have any questions, feel free to reach out. That's what I'm here for. Stay safe, and we'll talk again soon.